Today we are going to discuss about the crystal diffraction, and the crystal diffraction specifically we are going to discuss what is X-ray diffraction, which is XRD. So this X-ray diffraction is very important technique in case of crystal diffraction, because most of the structure of the solids are obtained from the X-ray diffraction. So what the most important and the basic law for the X-ray diffraction is known as Bragg's law. So before discussing Bragg's law, so in the course of waveguide optics, we have done the experiment of diffraction grating, in which we takes the uniformly spaced gratings. So you can also say that they are optical grating, because in that case the incident light is normal light. So in that case, when we incident the normal light on the these diffraction grating, we obtained a very fine diffraction pattern where there is maxima and minima. So in if you take incident light as a X-ray on that optical gratings, so there is no diffraction pattern, because wavelength of X-ray is not comparable to the interplanar the spacing between that grating. So you can say that the spacing between that diffraction grating is very greater than the wavelength of the X-ray. Therefore, there is no diffraction pattern obtained in case of X-ray. So this forms the basis for the X-ray diffraction. So in 1912, Maxwell law proposed that to observe the X-ray diffraction, the crystals can be considered as grating, or they can be used as grating to diffract the X-ray. So the first crystal was used to observe the X-ray diffraction was zinc blende or zinc sulfide. So the motivation to propose the crystal in case of X-ray diffraction, because crystal have periodicity and atomic lattice planes are parallel, and we know that the spacing between the crystals is of the order, you can say interplanar spacing between the crystal is of the order of angstrom, that is 10 raised to power minus 10 meter. And we know that wavelength of X-ray is also of the order of 10 raised to power 10 meter. So this is very basic motivation to consider the crystal as grating. You can also say that crystals are atomic gratings. So the spacing between the crystal, interplanar spacing between the crystal is comparable to the wavelength of the X-ray. So this was the most basic reason to consider X-ray for the X-ray diffraction. So the W.H. Bragg and W.L. Bragg, both are father and son. They study they consider this assumption and study this X-ray diffraction, and they comes up with the Bragg's law or Bragg's equation. And further, the Max Planck law also studied this X-ray diffraction, and we will further study the these laws equation or law spots. So first crystal was taken as zinc sulfide, or you can say that zinc blend. So now let us discuss the Bragg's law. In the Bragg's law, we consider the two parallel atomic planes of crystal which has the periodicity, which have the mirror indices HKL. Both are parallel, so therefore their mirror indices will be the same, HKL. So let us consider that an X-ray is incident on this plane and get reflected by this atoms in this atomic lattice. So and another X-ray is get reflected by this atom. So let us consider this is the glancing angle theta, and this also be the glancing angle theta, and this will be the angle of reflection theta. So since they are parallel, so let us consider this is the interplanar distance, this is d. So let us consider this babe as a p q, and this is b, sorry, a p a dash, this is b q b dash. So now since we are discussing the X-ray diffraction, so in case of diffraction we have maxima or minima. You can say that constructive interference or destructive interference. So also for the maxima you can say that the babes, the crest and trough of the babes are getting added up, and we get the maximum intensity spot, or as you can say that we get the maxima. So to get the maxima, we have the condition, that is the path difference is equal to n lambda. This is the condition for the for the maxima in diffraction. So we know that this wave is AP A dash, and both are parallel. So let us draw a perpendicular, and this also draw a perpendicular. So this is PM, this is P, this is N, this is perpendicular, we have drawn the perpendicular. So since this theta glancing this is theta, this also be theta, and this, if this is theta, this will be theta, this will be theta. So now what we have to find out the path difference, because now since the wave from here AP and this BM are both same, and PA and NB both are same, then what will be the path difference? Path difference will be MQ plus QN. So the path difference from here is delta. We have to find the path difference. This will be MQ plus QN. This is equation number 1. This is equation number 2. So now we have to find out the MQ and QN. So to find the MQ, let us consider this triangle MQP from this rectangle triangle MQP. So now we have to find out the MQ. This is perpendicular, this is base because angle this is making with this PQ, this is hypotenuse. So we have to find the perpendicular. To find the perpendicular, this MQ perpendicular upon base hypotenuse PQ is equal to sine theta. So further MQ is equal to PQ, this is sine theta. So MQ, since PQ is nothing but interplanar spacing between these two atomic planes, this is D, so this will be D sine theta. Similarly, we have to find the Qn. Similarly, from this triangle QNP, right angle triangle QNP, this is perpendicular, this is hypotenuse, this is base. So Qn will be Qn perpendicular, this will be P upon H. H is PQ. This is sine theta. Now Qn will be PQ sine theta. This will be D sine theta. This is question number 3. This is question number 4. Now by using equation 2, 3 and 4, we have, that is, delta will be, putting the value of mq and qn, this will be d sine theta plus d sine theta. So delta will be 2d sine theta. Question number 5. Now by using the equation number that is 5 into equation number 1, that or so you can say that putting the value of delta into that maxima condition, that is 2d sine theta, that delta, this is delta is equal to n lambda. This equation represents the Bragg's law. This is so therefore Bragg's law holds the very important and very basic condition for the that X-ray diffraction. So since sine theta less than equal to, always less than equal to 1, so therefore that is lambda is always less than equal to 2d. So therefore this is known as Bragg's condition for X-ray diffraction. Or also you can say that the Bragg's this X-ray diffraction will be hold only for d 1 angstrom and that is lambda should be 2d less than equal to 2d, or lambda will also approximately 1 angstrom. Only for these conditions this Bragg's law will hold. And from this equation you can also say that when that this intensity of that diffraction pattern is inversely proportional to n. As n goes for the higher values, that intensity decreases. So here this n is integer, so 1, 2, 3 higher value. So as n increases, intensity of that diffraction pattern decreases. So this is all about the Bragg's law. But Bragg's law holds a very big drawback, that this Bragg's law does not give any information about the intensity of scattering for that spatial distribution of electrons in that particular unit cell. And in this Bragg's law we have only considered that atoms of lattice planes, and we have neglected the interaction of X-ray with the constituents of the crystals, or constituents means bases, and that particular atoms in that unit cell. So that discrepancy of Bragg's law will be solved in Law's theory of X-ray diffraction.